Hey guys, let's keep talking about electromagnetism. We haven't got to the magnetism yet, but last lesson was parallel plates and how to produce an electric field there. But now let's keep thinking about that idea. Let's generalize it and talk about any sort of particle that is in an electric field. How will it behave? What sort of dynamics can we come up with from a particle that travels or charged particle in this case, as it moves around an electric field. Okay, so if we consider now, let's say we have two positively charged particles. Okay, one of them will be in our origin, in our frame of reference, this guy here. This will be the one that's not moving. And we're going to take another one at some distance r1 away from it, and we're going to move it to a new position, r2, along some radial distance. Okay, what's going to happen to the energy of the system? Okay, comparing this initial state here to this final state here. Well, we can consider energy, right? So we know that there's going to be a potential, an initial potential. Let's call it U1. This will be my initial potential. That's the potential energy when the second particle was at R1. Okay. Now that's going to be all the energy because it's not moving. They're starting off at rest. Excuse me, but they're going to repel each other, right? So when they repel each other, they're going to come up with a new kinetic energy afterwards here. We're going to lose some potential, and it's going to be converted to kinetic. Remember, we can't just have energy disappear, so we have to apply conservation of energy. So the initial energy, U1, is going to be equal to the U2 plus this new kinetic energy. Now if I replace the potential with my expression here for potential energy between two charges, notice it's over R, not R squared. That'll be the force. And this is my potential energy afterwards when it's at a new position, R2, plus half mv squared. I'm going to use delta v here because we're talking about a change in velocity and a change in kinetic energy. So that would basically mean the initially we're talking about v1 equals 0, but we'll use this as our representation of the new velocity. Now if I take this term here, R2, and I send it over to the left hand side, it becomes negative, and what I have here now is I have a change of energy, a negative change of energy here, which basically means that the energy that I lose, when I lose energy, I end up with lose potential energy. I've gained that in kinetic, which makes total sense. This is just an expression here of the law of conservation of energy. This is the first law of thermodynamics. Sorry. First law of thermodynamics. Right? That, we can't create or destroy energy. Now, let's use this. So let's consider a 3 microcoulomb charge. And we're going to put it next to a 6 microcoulomb charge. That one's not going to move. But the 3 microcoulomb charge is able to move. They are 30 centimeters apart, and they're going to start to repel each other because you notice they're both positive. What's going to be the velocity of the free particle, this 3 microcoulomb charge, when they've gone now to 100 centimeters apart, or 1 meter apart? Let's assume a mass of the moving charge of 160 grams. So how do I solve this? I know that I'm going to have my initial energy is going to equal to my final energy, right? Just like we did in the last slide. So my initial energy is just going to be potential. So that's going to be K Q1 Q2 all over R1. That's my initial, this guy here, this 30 centimeters, that's R1. And that's going to be equal to K Q1 Q2 over my new position, 1 meter, plus the kinetic energy, half mv squared for my charges. Okay, I can bring this guy over, and I can factor out the k and the q's. So I should end up with k Q1, Q2, all multiplied by 1 over R1, take away 1 over R2. I just did a couple steps there together. But you see I factored out the K, Q1, Q2 from these two expressions. This guy came over, so it became negative. I'm going to put this expression here, and I'm asked to find the speed of the free particle. So speed is going to be equal to 2k Coulomb constant, Q1, Q2, all over m, multiplied by that 1 over R1, take away 1 over R2, plugging everything in, I end up with speed of 2.2 meters per second. Please write this out, fill this all in, and check my work there. I'm pretty sure we end up with a speed of 2.2 meters a second once we've gotten to this new 1 meter position, right? Just I should have drawn a picture before, but remember, this is what we're talking about. 6 microcoulombs. We're starting off here at this guy, 3 microcoulombs, starting off at 30 centimeters, and then ending up at a full meter away, so an extra 70 centimeters, so to a new position here of 1 meter. Okay, so it starts off at rest, and it's going to be accelerating as it goes along. All right. So this was just using energy conservation, that the energy to begin with, just the potential to begin with, gets changed into a reduced potential because they're farther away, and a kinetic energy because it's now moving away because of the repulsion between the two positives. Okay. All right, so let's try another one here. So let's say we have a cathode ray tube. What the heck is a cathode ray tube? That's basically your old TV sets. The big TVs, not the flat screen TVs, the big old TVs. They worked by basically using an electron gun and then steering those electrons across the screen and coming up with a picture. All right, so the first stage of producing a cathode ray tube is making an electron gun. And this is how we make it. So we have 2 plates here. We heat up some metal. When you heat up metal, it actually gives off electrons. But we can't use them as they're just being launched everywhere. We need to actually give them a significant velocity. So we come up with this parallel plate set up here, and there's a little gap in between. So the electrons are produced, they're negatively charged. They're going to be repelled from the negative plate and sent towards the positive. The ones that are elsewhere just hit the positive, but the ones that are able to go through this gap get launched off with some velocity. Okay? So the question is, what is the speed of that? If the potential is 5,000 volts, that sounds like a lot for a television, but using a transformer, you're able to reduce the current and increase the voltage. So it's not that dangerous. But yes, that's what your typical TV would have, a quite high potential to accelerate these electrons. Let's find out how fast they actually travel. So initially, we have, right, initial energy equals final energy. But here we have only potential. We don't have any distance. All we know is the potential. But we've learned that potential really just means the energy per charge. Right? So if I know what the charge is, I can say that my whole potential energy is, well, let's just write that down. It's going to be the potential energy before converted into kinetic. But that initial potential energy is just going to be the charge multiplied by the voltage. Because remember, voltage really is, volts is joules per coulomb. This is a potential per charge. So if I multiply by the amount of charge that I'm pushing, I end up with a potential energy. And that's going to be equal to half mv squared. Okay, so then my velocity ends up being, hey, wait a second, I forgot something back here. Yeah. Remember, that's a half, right? Because I have to take the square root. But again here, so what am I ended up with? This will be 2q volts divided by mass and all of that to the power of a half. Working all this out, I end up with a speed of 4.2 times 10 to the 7 meters a second. As I said, very fast. Okay, not speed of light fast, not really. It's an appreciable amount of the speed of light, so more than 10% of the speed of light, but really won't make any major effects in terms of the mass. Okay, it's non-relativistic even at this stage. All right, so you guys can again plug in those numbers, see if I got that right, but I'm pretty sure we're good. Okay. Also, going back here, there should have been a half there. All right, so now the next stage of a cathode ray television, so we had our electron gun stage, which was in our last problem, but now once we've got these electrons being fired, we have to steer them across the screen to produce an image. And the way that you do that is with a this electric field at right angles to the velocity, because this will now aim it according to what the intensity is of that electric field. Right? In this case, it'll be positive. I'm launching an electron into here. It's going to be attracted towards the positive, so it's going to be steered off in this direction. If I flip the polarity of those plates, I could steer it in the other direction. Okay? So now that we have our electron gun firing these electrons, I can actually steer the electrons using a parallel plate configuration, just like this. Because remember, we learned in our last lesson is the electric field within this parallel plate setup is uniform, it doesn't change. Okay, so let's use this to calculate what the new velocity is of this electron. So before we start, let's call this the x direction, x hat. Let's call this the y direction, y hat. So this initial velocity here is, as a vector, is 2.5 times 10 to the 6 meters per second, and that's in the x direction. Okay, so let's figure out what that new velocity will be. So, I need an extra slide here. Okay, so I have an extra slide now. So I know how long this is going to be within the plates, because I know what speed it's traveling at, and I know what the distance is. So I know that my speed is equal to my distance divided by time. So my time, the time that it's going to be within that electric field, will be the speed, the distance divided by the speed. So the distance was 0.075 meters divided by 2.5 10 to the 6 meters a second. So a very short time interval. It's going to be 3.0 10 to the 8 seconds. It's only going to be in there for 30 billionths of a second. Very quick. All right, so I know my time. Next I can look at the force involved, because I know that my force is going to be equal to the charge multiplied by the electric field. Okay, I know what my electric field is. It's 130 volts per meter. If I multiply this by my charge, that'll tell me the force. And I know that this is also going to be equal to Newton's second law, the mass times acceleration. So the acceleration that this particle will feel will be equal to the charge. It's an electron, so charge on electron, multiplied by my electric field, divided by my mass of my particle. Plugging all the numbers in, I end up with an acceleration of 2.29 times 10 to the 13 meters per second squared. Now, I can also just make this a vector and say that this is in the y direction. Okay, so why is it in the y direction? Because it is a electron, it's negative, and it will be pulled upwards because the top plate was positive. Go back here. Top plate is positive. I'm putting a negative charge in here. It's going to be attracted. There's going to be a force in that direction, right? Because that would have been a negative charge, negative sign on the Q. E would have been down, so I end up with a positive vector up. Okay, so I have my acceleration. Now that I have acceleration, I have time, I can find out my new velocity. Let's say I call this Vy in the y direction. That's going to be my acceleration. Let's call it AY in my y direction times my time interval that I just calculated. Plugging those in, I end up with a new speed of 6.86 times 10 to the 5 meters per second, again in the y hat direction. All right, so that's how fast it's traveling now in the y direction. Right, it started off at rest in the y direction, but now we've increased its speed by sending it through this potential to a new speed. I've steered it in an upward direction. The question was, what's the velocity? So I can come up with a velocity. That's my Vy. I can say, if I want to cheat, I can say that my velocity is going to be 3.0 times 10 to the 6 x hat plus 6.86 times 10 to the 5 y hat meters per second. I can say that, but I don't like that. Let's if I use Pythagorean theorem, square those, take the square root, I end up with basically 2.6. Oh, sorry, that wasn't 3. No, that was 2.5. Sorry, this is 2.5. So I end up with 2.6 times 10 to the 6 meters per second, and it's going to be up, and my degrees end up being 15. Sorry, I was right. To the right, 15 degrees up. And to calculate the angle, just remember that's going to be 0.686 divided by 2.5, and whoops, this will be inverse tan of this. Okay, and that works out to 15 degrees, and there's my final answer. So I've steered this. So the point of this is I use the first example. I accelerated electrons, and now I was using when the electron was in the same direction. So if the electron is in the same direction as the electric field, it changes its magnitude of its velocity, and if it's at right angles to it, it changes the direction. So we can use electrons to speed up and to change direction of electrons or any charged particles. Okay, so that's why we spent all that time talking about parallel plates in the last lesson. They're very useful in generating a uniform electrical field that we can then use to either change the magnitude of velocity of a charged particle or its direction. Okay, so here's some more problems just like this. I'd like you to go through. Next lesson is actually going to be talking about magnetic fields, because magnetic fields can actually do this as well, because electricity and magnetism are basically the same thing. That's going to be fun. Okay, so hope I find you all well. Hope you guys are doing well, and I'm out. So I'll be talking to you later. Have fun.